Hello, so welcome to the Handshake Lemma from Graph Theory Speed Proof. So, what is Handshake Lemma? Basically, it's used to count the number of edges from the degree of the vertices. So, let's prove it. Okay, so we have a random network over here. So, looking only at this vertex, it has 1, 2 degree. Looking at this vertex, it has 1, 2, 3 degree. Looking at this one, it has 1, 2, 3 degree. This one, it has 1, 2 degree. This one has 1, 2, 3, 4, 5 degree. This one has 1, 2, 3 here. This one has 1, 2. Now, what we note, once we count all the degrees of the vertices, each edge is crossed twice. Therefore, we have, it is half sum of the degree of VI. There you go. QED. Now, yes, this was a speed proof, but let's sort of prove it rigorously now. So, basically, let me write the title. So, we will be proving the handshake lemma. So, let's suppose that we have a graph, because I love drawing graphs. So, we can represent graphs as matrices. First, we have the adjacency matrix. This basically is a matrix where it has 1 if Vi is incident to Vj and 0 otherwise, meaning that incident meaning they are connected by an edge. So you get, for this, you get that, you get vertices along here and vertices along here. Now, alternatively, we can represent graphs using what is called an incidence matrix. Incidence in... I wrote it wrong, didn't I? Oop. And an incidence matrix. Basically, unlike here where we had vertices as rows and vertices as columns, for the incidence matrix, we will have edges as rows and vertices as columns. Now, for this, we have 1 if vertex I is incident to edge I. 0 otherwise. Okay? So, let us represent this graph with some incidence matrix. So, we have this incidence matrix here. That's really weird. Now, along here, we have the edges. So, edge 1 up to edge M. Here, we will have the vertices. So, V1 up to Vn. Now, let's do a column-wise sum. So we sum everything in the array that's in the same column and write them as a vector over here. So every edge can only be incident to two vertices, because that's the definition of an edge. It's a pair of vertices connected. So let's say this one has 1, 0, 0, 0, dot, 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 1, 0, or something. All of these will be row-wise summed to 2. And we have m of these. Now, let's sum column-wise. Every vertex will have some amount of edges. Now, here we will have n, obviously, because we have n edges. N vertices, sorry. So, every vertex has the same amount of edges connected to it as its degree. Again, by definition. So, here we will have degree of v1 dot 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 degree of v2. Now, since we are counting the same amount of ones in this matrix, both here and both here, summing this up and summing this up should give the same thing. So, we get that sum of the degree of vi I equals 1 to n. Where did that come from? Whatever. This is equal, well, we have, all these are 2. There are m of them. This is equal to 2m. M is number of edges, which implies number of edges is equal to half the sum of the degrees. And there you go, that's the handshake lemma. Well, it's a fun fact. It got its name because, imagine you have, look at this. Imagine you have 5 people in a room and you tell them, go and handshake each other randomly. And then you ask each one, for example, let's start with this one. How many times did you perform a handshake? He says 1, 2. You ask this guy, how many times did you perform a handshake? He says 3. This guy, he says 4. This guy says 2 handshakes for me, bro. This guy, 3. But if you sum them all up, the total number of handshakes that were performed is half of this sum. Hence, handshake lemma. And that's the speed proof. So that was the speed proof. That's where this lemma comes from. And it's a very simple lemma, but I think it's one of the most important lemmas and the most useful lemmas in all of mathematics, because honestly, it's everywhere. I mean, wow, it's amazing, honestly. So, yeah, that's basically it. Thank you and goodbye.